So problem 6.1.3. Take a moment to read the question, and we'll get started. So we've got a painting. They give us the mass, two thin pieces of wire, each of a certain length. Connect the painting center to two hooks in the wall. The hooks are at the same height and are 0.330 meters apart. When the painting hangs straight on the wall, how much tension is in each piece of wire? So first of all, just get a little picture of what's going on. I've got a wire hanging down here and another wire hanging down here. They're both the same length. This distance that separates them is L equals 0.33 meters. And the length, well, I'll call this big L. And little l, the length of each side of the triangle, is 0.25 meters. And the picture is hanging here, so the other thing I want to draw is a force diagram that shows the forces that act. So mg is pulling down, and the tension in each string pushes to either side. Now I know the two tensions should add up to equal mg. I need to find out how big those tensions are in order to hold up the mass of the object. So first thing I'm going to need to find, in order to resolve tension into components, I need to know what this angle is. And I have to use the dimensions that I've been given to find this angle. If I split the whole thing in half like that, I get a right angle triangle, and this distance, that's half the distance between the two hooks. So I have the adjacent side here and the hypotenuse here. So adjacent over hypotenuse is cosine. Cosine of my angle is the adjacent, which is L over 2, divided by the hypotenuse, which is little l. So there's the cosine of my angle. I could use that to find the angle itself, but I might not need to, so I'm going to hold off on that. Now that I know the angle, I can look at my force diagram a little better. Draw it again. Tension mg. This is my angle theta. And the component of the tension that acts upward, because there are two ropes, one on either side, they're both going to push upwards. So this component only has to be half of the weight. So mg over 2, half of the weight pulling down, has got to be equal to the component of t that pushes upwards. I'll call that TV, t vertical, the component that pushes upwards. And if I look at this diagram, the vertical component of tension is opposite the angle. So the vertical component of tension divided by the tension itself, which is the hypotenuse, is going to be the sine of my angle. So therefore, I can write down that TV is t sine theta. So mg over 2 is going to equal the tension times sine of the angle. Which means I'm running out of space, but the tension therefore is going to be mg over 2 sine theta. So I'll have to figure out the angle from the cosine formula here, and then find the sine and plug it in. Note that because I'm dividing by sine theta and dividing by 2, well, because I'm dividing by sine theta, if the angle's small, sine theta will be small, and the tension will actually be very big. So if I have a very small angle, I'm going to need a very big tension to hold this up. And we'll just see how it comes out.